when we talk about membrane protein now, it's basically this membrane protein that actually or embedded deeply into, and they are facing the ECF and also into the ICF environment. So they are actually both. Yeah. So this membrane basically proteins able to do that. They going through. And now you look at the membrane's function, the membrane protein's function. So the most important function that it has is basically, there are many of that, but one of them is they function as a host or a transport protein. So we look at page, okay, we look at page 40. So if the membrane function as a pore, so a pore means basically they create channels. Okay, they are not gated, which means that they allow ions to flow out. And we know in the cell, they have high potassium ions, and basically they allow the potassium ions to go out. So these pores, they are basically quite specific. Sorry, somebody, anything? No. They are basically quite specific, and if they are allowed only, you call this pore as a leakage channel for potassium, or the pore for potassium, so they are also known as leakage channel, which means they only allow potassium to actually go out, or pores for potassium. Okay, or you might have, if that is the case, why does the potassium actually go out from the cell into the ECF? Why does the potassium move out from the cell?
I think it's because of the concentration gradient between potassium and sodium.
Yes. So the concentration gradient inside the cell is much, much higher than those outside the cell. And we know they are around 140 millimole inside the cell per liter, and here is around, let's say, 4 millimole. So which is very much lower. So the potassium move down the concentration gradient. They understood. So that means it moved from the outside to the inside to the outside of the cell. Sometimes we call that the efflux of the cell. The efflux, and basically the efflux out of the cell. Okay, so this is basically their function as a pore, or then you look at channels. So they can, sometimes these membranes can function as a channels. So this is about pore. Okay, if they function as a channel, that means they are usually gated. So if they are gated, we still use potassium. That means now you have the potassium gated. So let's say they are gated potassium. Okay, or they can be also gated. Let's say they can be also gated sodium. Okay, which means that they have gate, and this gate can either close or they can actually open. Yeah, so the gate can be closed or open. That depends on the gate. So if let's say the gate is open, certain thing change it, so it allow sodium to actually move into the cell. Yes. Anything? Akash, you are on your video. That's very nice. You enjoy yourself. Akash.
Sorry, doctor.
You're enjoying yourself. No, it's okay. That is part of life when you do online teaching. Yeah. Why does the sodium move into the cell rather than out of the cell when the gate is open? Anyone?
Because there is a
What's the
low
question?
concentration of sodium inside of the cell.
Sorry. Yeah. Koba says that because the concentration of sodium outside the cell is higher compared to inside the cell, probably also around 5 millimole. Okay, so it's about 5. So sodium basically move down the concentration gradient. My question is, why does the sodium move into the cell when the gate is open? Yeah, and when this gate open, and then let's say we say this is a voltage gated, yeah, voltage gated channel for sodium. So if there's change in volt, this gate is able to open and allow sodium to basically move down the concentration gradient into the cell. Yeah. Okay, so we basically talk about these two now, the pores and also the channels. Okay. So we have both of these, then we have a carrier. What happens now? It functions as a carrier. Okay. So carrier, we can talk about the ion channels, basically the sodium potassium pump. So far, are you all clear basically about pores?
Yes, doctor.
Okay. Now, if it function as a carrier, so it start to carry. So we look at sodium potassium pump. So there's a nice picture there, basically to show you about the transport of this. Okay, it's able to transport in 3 potassium and move out 2 sodium. Sorry, we move in 2 potassium, transport out 3 sodium. Okay, which means that this sodium potassium pump, there is sodium potassium pump, or sometimes they are known as ATPase, because they require energy, which means that intracellularly is able to use ATP to open the gate. So it becomes a carrier. So it carry out 3 sodium and put in 2 potassium into the cell. So this is a sodium potassium pump that acts as a carrier. Okay. Okay, but some of the carrier can be facilitated. Okay, or some are become a facilitated carrier. Okay, we look at this is primary, basically the primary sodium potassium. This is primary active transport, active transporter. Okay, then you have the secondary transporter, where basically is going to transport sodium and also together, let's say glucose. So this is known as secondary active transport. Transporter. So it basically transport both sodium and glucose into the cell. Okay, why does the sodium and glucose able to come into the cell and is known as secondary active transport? Sodium is going down the concentration gradient, right? We know that sodium come into the cell because the intracellular, the sodium level is low, so it basically come in and it carries together also the glucose that is coming into the cell. Okay, so they are known as a transporter. Or you can have a carrier that is a glucose transporter, which we talk a lot about. Let's say we talk about GLUT4, which are basically a transporter that only carry in glucose. Okay, so this is known as glucose transporter, let's say 4, and they are insulin dependent. If you are glucose transporter 2, they are non-insulin dependent. They don't depend on insulin. They are present on the cell membrane of the cell. Okay.
Doctor?
Yes.
You said that the sodium moves in the cell because there are lower sodium inside the cell.
Yes.
How is that while it's active transport?
Okay. This is active transport because it depends on the primary transporter. Okay. you look at the primary transporter, the sodium potassium pump, basically moves sodium out. You take out 3 sodium molecules and you took in 2 potassium molecules, and it utilized ATPs. That means it used ATP to become ADP. Okay, with the energy, it is able to transport the sodium against the concentration gradient. That means against, here, you know, it's basically high, and here potassium is high. So they are against the concentration gradient. That's why they need energy. Okay. Adil was asking how you consider that as a secondary active transport, because it depends on the primary pump.
How
Okay,
does
Adil?
it depend on it?
Because it depends on the primary pump to move the sodium against the concentration gradient.
Oh, so for the sodium, it is active transport. For the potassium, it's passive.
No. For the sodium and potassium, for the primary pump, they are both against the concentration gradient. You see that? It pumps 3 sodium out into the cell, outside of the cell, the ECF. Because the ECF has very high sodium, it takes in potassium, which is also very high inside the cell. So both ways, it goes against the concentration gradients. And this is the primary active transport. And you require ATPs. That's the energy source. Is that okay, Adil?
Yeah, I understood. Thank you.
Okay. Sorry, I
It's a
just
sodium potassium pump, right, doctor?
Yes, Akash. This is sodium potassium pump. But the secondary active transport depends on sodium. Okay. You know that sodium basically comes into the cell down the concentration gradient. Okay. And glucose can be against the concentration gradient or down the concentration gradient, but it doesn't matter. Let's say it go against the concentration gradient, which means that there is glucose here, and here have higher amount of glucose, and glucose can be transported in down the concentration gradient, and it can become part of the facilitated, just like a glucose transporter. Yeah. So in glucose transporter, usually the glucose level in the ECF is higher compared to inside the cell, so the glucose can be transported down the concentration gradients. Is that okay? But in the secondary active transport, the glucose can be transported against the concentration gradient because it utilized together with sodium, and sodium is actually down the concentration gradient. Okay, but it works together with the sodium, with the active transport or the primary transporter. Is there confusion? Do you have any question you want to ask now? No. Okay. We can talk. Okay, we can talk more later if you have questions. In next Monday, we will talk a lot about the this transporter, because how the solute can be transported. So we have done both the pores, the channels, and also the carriers. Now, if I'm going to ask you a question, okay, what is pores, channels, and carriers are?
What are pores, channels, and carriers?
Carriers, yes. So you can give answers, or you want give me to give you an option.
If I were to give it,
Yeah, short answer questions.
They're transport proteins.
So they are basically all are transport proteins.
The channel protein transports it
Okay.
in like through a channel, while the carrier binds to ions.
Okay, good. So basically they are all ion transporter. Is that true?
Yes.
Yes. Okay. But if they are secondary active transport, that means they can transport glucose. So they are not ion transporter only. They also transport molecules. So that might not be true lah. Yeah, Safwan.
Okay.
Okay.
Okay, Doctor.
Yeah. Okay. They all utilize energy source for their transport. Is that true?
No.
No, because the pore doesn't. And even the channels, they don't. Only the carriers or primary active transport is the one. They require energy. So they are not all the protein channels that transport molecules or ions that require energy. No. Okay. And all the pores channels and carriers transport the energy down the concentration gradient. Is that true?
No.
No. No. Because the primarily active transport, they transport against the concentration gradient. Right. So these are the things that generally we will ask you to make sure that you can differentiate between the channels and also the carriers. Yeah. Okay. So if you do that, then you should be able to do the activity 5.17, page 43. Okay, you look at it and then is there any question you want to ask? Is there any question you want to ask? No. No. Anyone put out a hand? No. So no question on this.
I have a question.
Yes, Walker.
So the channels, they open and close depending on stimulation, is it?
Yes. When we talk about channels, basically they have gates.
Okay, so stimulation like nerve
Yes.
stimulation.
If they are stimulated by, let's say, by change in membrane potential, so we call that voltage. So they are voltage gated channels.
Okay, thank you.
Okay. If they are opened by chemicals or ligands or chemicals, so we call them chemical gated channels. Or sometimes by stretch, mechanical. That means if there's mechanical stimulus by compression or anything less like your touch. Okay. Basically, if they are mechanical, then we call them mechanical gated channels. That's physical. That means they are mechanical gated channels. And you find that a lot in your touch sensory receptor. That's where they open up to touch. There's a change in the pressure. It actually open up the mechanical gated channels that allow sodium to get into the cell. Yeah. Any other questions? If you don't, I'm going to ask you. Okay. Look at the last question in activity 5.1. What is the most important characteristic of the ion pump? Can anyone want to try?
I don't know if it's a characteristic or not, but
It's okay.
it carries a certain amount of ions, like 3 sodium and 2 potassium.
Okay. That when you refer to a sodium potassium pump, what happens if there is an ion, is a hydrogen pump that in the present the epithelial cell of the stomach? Okay. Anyone? Yes, Safwan.
The most important characteristic of an ion pump, their active site. Their active site, yeah.
Yes.
I mean their binding site. Right.
Okay, their binding site. They have binding sites. Yeah, Walker.
Is it that they're able to carry against the concentration gradient?
Yes, that is also one that basically they are carrying molecules or ions against the concentration gradients. Yeah. Ikoba, you have anything you want to say? Muhammad Ikoba.
No, doctor. I was going to say they carry the ions against the concentration gradient, which already been said.
Okay. The most important things, all these ion pumps, basically they carry the ions. That's one important. But when you talk about pumps, that means they utilize energy source, which means that they are able to break down ATP for the energy source. That is where the most important characteristic of an ion pump. So all ion pumps will use ATPs as the energy source. So sometimes they are known as sodium potassium ATPase, or they are known as hydrogen ATPase, or they are sometimes also known as calcium ATPase or calcium pump, which basically they use energy. So anything we talk about pump, that means they must be able to use energy, just like our water pump or electrical pump that basically require electrics to run the pump. Yeah. So all the ion pumps, they require energy source, that is ATPs, or they are able to break down ATPs for energy. So okay. So I have give 3 examples that of the ion pump. That is basically the sodium potassium pump, okay, the hydrogen pump, and also the calcium pumps. Do you know where they are located? Sodium potassium pump. Anyone? No. Okay. All the sodium potassium pump are always located on the basolateral side of the cell. Okay, so if you have a cell, I just rub this off. Okay, most of the cells, epithelial cell, any cell. Yes.
Doctor,
Yes.
did you open your video yet or not? Because I can't
Yes.
see.
Oh, you can't see. Yes, it's already on. You can't see that?
Yeah, okay.
Okay. So for any cell that is present, there's an epithelial cell, and you have a lumen. Okay, they will always have 2 sides. This is the luminous side or the apical side. Sometimes they are known as apical. Okay, and the basolateral side. Okay, so this cell membrane on the basolateral side, that is where the sodium potassium pump is always present here. Okay, basically they are all present here. Okay, they have implications, basically sodium, potassium, 3, 2, right? Why is that important that the sodium potassium pump must be located on the basolateral side? This is where most of the filtrates or materials that is getting through. Yeah. What is the implication that it must be located on the basolateral side?
So they can get the molecules to pass through without getting through the phospholipid spiral.
Okay, so basically it can help to basically allow the ions to be transported. So this is still in the ECF. And remember that? And this is the ICF. Okay, some of this is the external environment. Let's say in the intestine, it becomes the external environment. And even the kidney, they are considered the external environment because in the lumen, yeah. So they are in contact with the external environment. And all these are very important because the sodium will always be maintained high in the ECF and potassium is high in the ICF. So it can actually allow, let's say there are sodium to be reabsorbed. So sodium in the external environment can be reabsorbed. But let's say the filtrates in the kidney, you have a lot of sodium that need to be reabsorbed. Sometimes you filter out glucose, so it can be going through the transporter, can be reabsorbed. So glucose can also be reabsorbed together with sodium, so it becomes a co-transporter. Okay, if the side is over the other side, is it sodium potassium on the luminous side, then it becomes a problem. So it starts to secrete sodium out. If it's here, then it's going to secrete sodium out and you are going to lose sodium rather than actually save or reabsorb the sodium. Yeah. Is that okay? So for sodium potassium pump, they are always on the basolateral side, except there are one place where the sodium potassium pump of the cell is located on the luminous side. Okay. Later on, you will find out where they are. I'm not going to tell you now. You can Google it if you like to know. But it's important, especially for the same thing as transport of fluid. Yeah. So when sodium actually being transported across, so if you are able to take in sodium, what happens to the water? It will also follow sodium. The same thing as chloride. Okay. Because to maintain the negativity, so sodium chloride will be reabsorbed. Basically, you also taking water. Yeah. But that is later we talk about the transporter on Monday. So I just stop there. Okay. Now, where is the hydrogen pumps located? Where can you find hydrogen pumps? Okay. Anyone? No. You can Google that later on. It's okay. Same thing in the in the stomach is on the luminous side, so that it can pump hydrogen ions out. Okay, so you have hydrogen ions on the cell that is generated. How does the hydrogen here generated? Is because it generated from carbon dioxide plus water, okay, to become hydrogen plus the bicarb. So you can actually, plus bicarb. So that can be actually shared or transport out to become part of the buffering system. Yeah. So the cells that are present on the stomach. Okay. They are mostly present there, and you want to create a very high environment for acid for digestion. So hydrogen chloride is being formed in the stomach for digestion of protein. Okay. So that's done. Then where are the sodium potassium pump the calcium pump? Okay, the skeletal muscles, the cell, so they have this sarcoplasmic reticulum. Okay, and most of this is where you want to store the calcium into the sarcoplasmic reticulum. So all these calcium pumps are located here, or you want to also take up calcium into the environment. But this is not very useful because it help to reduce the calcium level after the contraction. But most of them are basically stored in the sarcoplasmic reticulum of a muscle. Okay, we will talk that later on when we do skeletal muscle and also smooth muscle. So I already give you the 3 examples of the ion pump and state their location. Yeah. Any question on that?
Doctor?
Yes.
Is the hydrogen pump also present in the in mitochondria?
In mitochondria.
Yeah. Is it considered a hydrogen pump?
Yes. Some of the they have this hydrogen transporter. Basically, yes. They allow the ions to be basically moved down the chain for generation of ATPs. Okay. But I specifically looking at the system where they are located.
Okay, thank you.
Yeah. So now look at it function as an enzyme. So there are many, basically, we know that in the small intestines, these enzymes are present. So when you look at the small intestine, the epithelial cell or the small intestine, okay, they have this surface enzyme. So this is the luminous side. So the GIT, the digestive material are all present there. So the enzyme is present. That is the lactase. Okay, or sometimes even the sucrase. They are present on the surface of the epithelial cell on the luminous side. Okay, Why is that important then?
They break down the molecules into the simple sugar.
So the most important thing, they are carbohydrates, okay, digestion, so that it can be broken down. What happens if you secrete the enzyme into you secrete the lactase into the environment, inside the GI tract? There's lactase there, basically also break down. Can that happen? Yeah, it can happen, but it's not good in the sense that this will be broken down and into the individual molecule. You have lactose, basically become galactose and glucose. So all this glucose that is formed will be used by the bacteria. So we know a lot of bacteria will like that. So this epithelial cell basically created by Allah or God, that they have surface area here. So when they breaks down, the glucose will be immediately absorbed into the cell. Okay, and we know how they are being transported. You have glucose now. When they have that, they will be transported by the sodium glucose transporter. Is that okay? And then over this side, they have the glucose transporter that basically take out glucose. So usually they are group 2. So glucose is transported, okay, out into the ECF. Is that okay? So there is one about the enzyme that is present on, so they are very important. Then you have the enzyme called ACE, converting enzyme, angiotensin converting enzyme. That is basically on the pulmonary and endothelial cell. They are very important to convert angiotensin 1 to become angiotensin 2. Yeah, and you have adenocyclase and also phospholipase C. So these are that we are going to learn them more as you go through. Okay, so you can work on activity 5.18, membrane bounded enzymes and how they actually helps to actually do that. Okay, you look at question on 5.18, that is page 45. Which cell have sodium potassium pump?
The plasma cells?
The plasma cells. Okay. Any other cells other than the plasma cells?
The epithelial cells.
Okay, epithelial cells. Only epithelial cell, plasma cells. Waka? Waka? Is only these two types of cell have sodium potassium pump?
No. Most of
Okay.
other cells.
Okay. All our body cell must have sodium potassium pump, even including the RBC. So basically, all cells have sodium potassium pump, and as I say that they must be located on the basolateral side if they are facing the lumen. If not, then generally they are present on the cell membrane of the cell. Why? Because all cells have membrane potential, and this sodium potassium pump help to maintain the membrane potential. Yeah. So how does the pumps work? You already know what it is considered as a membrane enzyme because it can break down the ATPs because it has ATPase. Is that okay?
Yes, doctor.
Okay. Yes, Afwan. Okay, so we are done with the 5.18 unless you have a question. If not, we look at the receptors. We are going to talk about this in module 7 about intracellular communication, which means that it's very important that the cell must have a receptor. If the cell doesn't have a receptor, it cannot communicate. Just like now, for us, you must have a handphone. Without a handphone, you are lost. Is that true? I enjoy the cell as a square. So the cell, they always have a receptors on the cell membrane, and these receptors must be able to receive information or chemicals information basically. So it must have a receptors that is able to receive the information. So this information basically must be circulating there. So it must be able to attach to a receptor and basically allow the communication to occur. Okay, so the cell membrane must have the protein receptors. Okay, they are usually, or they have a receptors inside the cell. So we have both, either a surface membrane protein receptors or a cytosol membrane receptors. So they are both referring to usually the membrane protein. All of them are related to molecules that are not able to diffuse into the cell. So if molecule can diffuse into the cell like steroids, okay, then they basically has a cytosolic receptors. Those protein molecules that cannot diffuse to, they always have a membrane protein receptors that is present on the membrane. Still okay? Yes. You have a questions? Okay. Akash, we get you. Okay. So I thought you have a questions, no? Okay. Then anyone have any questions? So we can look at the membrane receptors and then we can see that how they actually works on here.
No questions.
No questions. Okay, so we can move on. Basically, we know that if you have an ADH that is released from the pituitary, it must be able to find its receptors. That is basically the ADH receptors. Okay, to be able to be stimulated. Okay, and allow cell communication to occur, and mainly to open up the aquaporin, or basically for water to basically move through. So you allow water to be reabsorbed. Okay. So this is how it works. Basically, it's able to translocate the aquaporins and inserted on the luminous side that allow the water to be reabsorbed by the cell. And this, you know, that they are very important in the distal tubule epithelial cell, yeah, for reabsorption of water. Okay, so we already done that. So you can work on the activity.
Doctor, sorry, I guess you're unmute. You're mute, sorry.
So it unmute itself. I don't know why sometimes it just unmute automatically. So I hope you understand about the ADH and how it basically work on the cells. Yeah, and these are basically found in the distal tubule cell for reabsorption of water in the filtrates. Yeah, on the nephrons in the epithelial kidney. Yeah. Okay, so you can work on activity 5.1. That's on page 47. Okay, so I just leave that to you to work on that, and then we will talk a bit more later on about this when we do transporter. There will be a lot for us to discuss. And can you turn to page 48 about protein molecules that become the linkage? Okay, so there are a lot of these membrane proteins that basically help to hold the cell together. Okay, so when you look at the membrane proteins, some of them become the tight junction, okay, or some become the gap junction. So importance is basically some of these epithelial cells, when they are work together, they will have a formation of these tight junctions, okay, so that the cell can basically hold together and form a continuous layer. Okay, that prevents molecules or ions that pass in between the cell. If there is no, okay, sometimes it can just go transcellularly. So some of these can actually go through. Yeah. So they have tight junctions and they has basically desmosome, okay, But some cells, they basically have gap junction. Some of the cells, they have gap junction that allow ions to actually move from one cell to the other. If you have a sodium here or you have potassium, so you are allowed, let's say sodium is able to come in, then you have sodium to basically cross over. So this is the gap junction. Okay. So you can work on activity 5.20. You have any question on that? No? Okay. Then the last one we are talking about is cell recognition protein. So we talk about basically how the cell is able to recognize the others. So we have some glycoprotein basically acts as a for cell recognition, and they are very important because without this recognition, because your immune system might probably attack the cell. So you have to basically cell recognition. Yeah. You are able to do that. The cells are able to do that basically to recognize another cell. So it based on the MHC protein. So this is major histocompatibility protein. Yeah. So I leave that because that is basically if cell explains in the module, so you can work on the activities on that. So that's all about the cell membrane. So you have a lot of these types of proteins that is basically present on the cell membrane. Is that okay? So you can do the summaries on that in page 52, activity 5.22. Okay, we are done with the cell protein now, cell membrane proteins. Okay, then you have, we turn to page 53 on
Doctor?
basement membrane. Yes.
Did you explain the cell recognition?
Sorry, I didn't get you. You are breaking off. What is the question?
Oh, did you explain the cell recognition?
No, I didn't. Because basically I say it's in the module, you can actually read on that. Cell recognition, basically they are surface protein that allow the immune system to recognize that the cell is a cell. Okay, and it also allow certain molecules to know that foreign molecules like bacteria or viruses that they are abnormal molecules. I think my internet is not very good, so it was turned off.
Okay, doctor.
Yeah.
I will note it.
Yeah. So you can read about it, so about cell recognition, yeah. And basically, when you do immunology, this will be a very important portion that you have to understand. How does the cell recognize that the cell, the body cell, is own cell, and why some cells or one immune cells suddenly decided to attack your beta cell or destroy some of the beta cell, or that happens when certain things happen. Yeah. So we move on to the next one, looking at the basement membrane. As we say, all these cells, just using the same one. Yeah. So I just turn on my video. Yeah. So some cells, all cells, they must have a basement membrane. I just use a different color. And this basement membrane are basically at the base of the site of the cell. That's why we call them the basolateral site. This is the basolateral site. This is the luminal site. Yeah, that facing the lumen. Okay, and all cell will have this this basement membrane. Okay, this is a layer, and mainly they serve the function is mainly for the cell to be able to attach to it, and it mostly contains thin fibrous extracellular matrix. Okay, so I can leave that to you to basically read. There are quite a lot of details things there, and you can work on activity 5.23. Is that okay?
Yes, doctor.
Yeah. You can turn to page 55 and you can work on the activities. Basically, it's there to work on the activities, and you can see that basically there are important structures there. Very, very detailed and very molecular. Okay. And the cell, for the cell to basically contact with the outside of the cell, they basically use integrin. So here the cell has a protein called integrin, which basically allow it to basically communicate with the outside. Yeah, integrin. They have a direct contact with the basement membrane, so they are the one that basically inform the cell what is going on outside the cell. Okay, it's integrin. Yeah. Okay, so I leave that to you, and then diseases related to the basement membrane. Also, you can turn to page 57. There are many diseases such as good pasture syndrome. Okay, so that you can actually work on that, but I don't want to go into all the diseases. No? Okay, so now we look at page 58, cell environmental interaction. Okay, we have some specialized cells in our body that have receptors or sensor, and you know basically they are able to sense our external environment. Yeah, so you have specialized cells that basically able to see light. So you have your eye, so they have a sensors or the receptors there to basically able to sense the light. And you have the ear, the hearing to basically look at sound. So all the five senses are basically specialized senses that you have. Yeah, some have even the sixth sense that you have when you feel something that is abnormal. Okay, so you have the special sixth sense, but most of the time we don't recognize that. We just recognize the five senses. Okay, then you have, these are mostly the external stimuli that you sense, but there are also some that you can sense by sensing a change in pressure or temperature. Okay, that is present on the surface of your skin. Okay, so you have a sensation of touch. Okay, or also change in temperature. So you can actually feel cold if the temperature is cold outside, or you can feel warm if the temperature is hot outside. Yeah, so that is the things that you have. So there are the extra senses like touch and also the temperature. Then the internal stimuli that you have, they are able to sense temperature in the internal environment. So you have the thermoregulatory receptors or thermoreceptor that is in the medulla, and you have stimuli that are receptors that is able to send the blood pressure, so baroreceptors. Then you have the chemoreceptors, yeah, that change looking at the osmotic pressure, or chemicals, basically looking at the pH and also the oxygen and partial pressure of carbon dioxide. Okay, so you can list down the details of that. Is that okay?
Yes.
Yes, Shafwan. Okay, there is one part on activity 5.25 looking at the significance of cell membrane structure in fertilization. So you can actually work on the activity, because basically it look at how cells these sperms able to get into the ova, and how it actually help during fertilization. Okay, so these are as important example looking at oval interaction with the sperms during fertilization. So I leave that to you to work on that activity, because that will be very important later when we do reproductive systems. So we move on to the next one. That is page 61 about pharmacological significance of cell membrane. Okay, and we know now most of our drugs, they are basically small molecule. The drugs that we took or we use to treat our patient, most of these drugs are basically small molecules that introduce into our body. Okay, and these drugs, most of it basically acts on the membrane proteins. Okay, even bacteria, viruses that get into our cell also basically works by interacting with these proteins. Okay, so we can actually divide the proteins into 4 categories that look at receptors, ion channels, carriers, and even enzymes. So you can actually work on that. And then they are also page 62, look at the flow chart, the figures, the pie chart, looking at how the type of protein that can serve as the drug targets. So almost 13% of the drugs, they target the receptors. Okay. And then there are ion channels, and also looking at the G protein couple receptors, there's 19%. Okay, so you can work on that. If you have any question on activity 5.26, we can discuss that. If not, I will just move on. You will do a lot of these drugs when you do pharmacology. Okay, so drugs can either become, if it works on the receptors, they can become agonistic or antagonistic. That means they can work against or act as agonistic as the receptors. Yes, are there anything?
Doctor, what is the third one? The effect on the cellular function?
The effect on the cellular function. Yeah, the third one. Which
Yeah.
one you're referring? So whatever that the cells, basically they have a receptors. So all this will be communicating to the cellular function. That means the receptor will basically either it become an agonistic if they are activated by the drugs, then they are known as agonistic drugs. Okay, that is usually affecting, increase the function of the intracellular inside the cell. That means it actually affects the cell function. They either increase the cell function, then they are agonistic drug. If they decrease the function or the response of the drug of the cellular function, then they are antagonistic. Is that okay? Or they prevents the cell from reacting to that, then they become antagonistic drugs. Is that okay?
Yes, yes. Wait, how do you pronounce that? Antagonistic.
Antagonistic. Antagonistic.
Okay. Thank you.
Yeah, that's right. So you have agonistic drugs. Okay, or antagonistic drugs. Okay, this generally will increase the cell function usually. So if the cell, if they say the drugs acts on the cell based on the receptors, it will either increase the cell to produce more proteins or more enzymes or even more, let's say, insulin. Okay, anything, or even more proteins or more hormones. These are agonistic drug. But antagonistic drug, it will basically reduce or stop the cell function. So if it works on the cell, basically the cell is not going to do anything. Basically, it stop functioning, the cellular function. Is that okay? So this is basically the agonistic drugs. Yeah.
Yes, thank you, doctor.
Okay. Then you will come to the drugs that acts on ion channels. So there are many drugs that actually can act on ion channels. So they broadly divided into either a blocker, opener, or modulator. Most of the time, we use the drug mostly for blocking. So you have a drugs that actually works by blocking the effect of an ion channels. Okay. So you have a drug. There is an ion channels here that open up when they are activated. So let's say allow sodium to come in. Now you have a drugs that actually block this. So sodium is not able to come in, so you cannot depolarize the cell. Okay, so there will be no action in this case. So you can actually stop that. So they are usually known as a blocker. Now, just an example. And you look at example that is given on page 67. Okay, the paragraph number 2, we talk about lidocaine. Okay, lidocaine is also one of them. Basically, it blocks the sodium channels. Lidocaine. If it blocks the sodium channels, so the sodium channels cannot be opened. Basically, it prevents the transmission of action potential. So basically, the nerve transmission impulses, so there will be no pain. Yeah. So there are many examples that have been given. So I leave it for you to read on that, and then you can work on activity 5.28. Okay, so you can actually get your answers from the modules. Yeah. So okay, look at activity 5.28, page 68.
Yes.
Okay. So we move on to the next one. Drugs that acts on carrier protein. The same thing, it can actually acts on the carrier protein. Okay. Example given is a furosemide, which is a low diuretic. Okay. You have the low diuretic. Over this side, the descending basically allow water to come in, and over this side it allows sodium, potassium, and chloride to be absorbed. So there are transporter here that allow this to be absorbed into the cell. Here, basically only water. Yeah, this is your glomerular filtration. Okay, so fluid will be filtered through. That is going to go down. Okay, and you are going to reabsorb sodium, potassium, and chloride. What happens if you use a drug that acts on this? This is called low diuretic, that basically inhibit sodium, potassium, and chloride from being absorbed. So the sodium basically in the cell will inside the lumen will start to increase, and basically it's going to hold back the water. So the amount of urine produced will increase. Still understood? When did you use this drug?
Doctor, can you explain this part again? How the urine increases?
Okay. If you give the drug, this is basically furosemide. This is a low diuretic that blocks the sodium, chloride, and potassium and chloride from being reabsorbed. So the content, I just make it bigger. Okay. If you block that, that means the content of sodium inside here will increase in the fluid, in the filtrates. Okay. This is going to basically attract water. It's going to basically, because it cannot be reabsorbed, the sodium. Okay, so now you are going to retain water. So the filtrates that come out later will be a lot of urine. The volume will increase because it contains a lot of water and also the sodium. Is that okay, Adil?
So it attracts water because the osmolarity decreases?
No, it prevents there is a transporter here, so I just make it bigger. Normally, this transporter is going to transport sodium, potassium, and also chloride. 3 molecules. So they are the co-transporter that is present on the ascending lobe and in the lobe of Henle. Yeah, okay. So now you give a drug. Okay. Where does the drugs work? Okay, these drugs basically now block the absorption or reabsorption of sodium, potassium, and chloride. So the sodium is going to be high, potassium is going to be high, and also chloride is going to be maintained inside the filtrates. Right. And we know that sodium, chloride, they become the salt that is going to be give an osmotic that is going to retain water. So now, whatever that comes out will contain a lot of sodium plus water, chloride. So that's why the urine increases. Is that okay?
Yeah.
Okay, good. Now, I'm going to ask you is, when are you going to use this drug? Can you give an example? When you want to get rid of the sodium in the ECF.
High blood pressure.
Yes, when you have very high osmolarity in your ECF, which means that if you look at the ECF, sorry, I have to draw the chart. So you have ECF, the ICF. So if the sodium content is high, right, it will basically increase the osmolarity in the ECF, which means it's going to increase the water. And this is basically going to cause increase in blood pressure. Is that okay? If sodium is high. Right. So what can you do? You can either stop or you use a drug to increase excretion of sodium and water. So this is where you use diuretic to why? Control the blood pressure. Is that understood?
Yes, doctor, but last time you said if you have high osmolarity, you can regulate this by two ways. One of them is drinking water. So if you
Yes.
can't drink water to remove this, why are you using the drug?
Yeah. That's why I say natural physiologically you can do by basically add water. So you drink. Right. Or
Yes.
you increase secretion of ADH. I mean, the pituitary gland will do that lah. Yeah. But if all these fail, what can you do? Okay, you can give a drugs that basically block this channel, and this is known as lobe diuretics. Okay, so that you can actually control the blood pressure. Is that right?
Yes.
Okay.
Thank you, doctor.
Okay. Yes, there is actually another blocker for sodium, but we want to look at this, the blocker there here. Basically, there's another blocker that you can block here. Okay, this is spironolactone. You can block there. Basically, also helps to basically prevent sodium from reabsorb, but it's on the distal tubule. Same. Still okay? They are different. What is the difference between this and this? Okay. The difference between this blocker and here is here it spare the potassium. Here it doesn't spare potassium, it will together excrete out ash. So if you're going to use the lobe diuretic, what will be the consequences? You are going to reduce the potassium level in the ECF. What is the consequences? Now more potassium is going to come out from the cell. Okay. What will be the consequences? The cell can become hyperpolarized. Or you can, because more of this coming out, it become hyperpolarized, or you can actually take in more hydrogen ions, which I'm going to explain later. Then you will have less hydrogen ions here. You can cause alkalosis. So these are the conditions that can be very important when you give drugs to a patient. So you can actually cause a lot of problem rather than just actually solve the problem. But I just make it simple, yeah, so that you can understand. Okay. So far, are you okay with this? So if there is a problem of potassium that is very important, then you can use this drug to basically block only sodium from reabsorb. Then you can also cause a diuretic. But here is 20% that you block, which is very fast. Here is probably about 5 to 10%. So it's very slow. It will take a bit longer time. So later on, when you do urinary systems, this will be explained in very detail how this drugs actually works when you do pharmacology. Yeah. Okay, I'll just stop there because if I go further, you might probably get more confused. Okay. So there is about the activity on drugs that works on the carrier proteins. Is that okay? And you have actually page 71, some of the nice pictures that show you how furosemide actually works. Yeah. So I leave that and you try to digest. If you have a question, you can always call me. Is that okay? Then we look at drugs that works on the enzyme. Page 73, drugs that works on the enzyme. And these are common drugs that we took. For example, the paracetamol, or that are commonly we take are basically the paracetamol that we took. And also aspirin, but aspirin is not commonly now taken by us. So the paracetamol, basically the non-steroidal anti-inflammatory drugs, basically they works on inhibiting the COX enzyme that convert the arachidonic acids to become prostaglandin. Okay, so that is how it actually works. So you can look at page 74 on activity 5.30. Okay, this is very important. We talked yesterday about fever. You know that in fever, there's increase in prostaglandin that is being formed. Okay, so if you take Panadol, that's how it suppress the prostaglandin production or reduce the prostaglandin production that help to basically bring back our temperature, body temperature to normal. Is that okay?
Okay, doctor.
Okay. So you can look at it, but there are two mechanisms that you can work on. They're basically COX-1 and COX-2. I will just leave you to work on the activity 5.31. Yeah. Unless you have a question, if not, I just move on. Okay. Drug that acts on the synapse. So there are also drugs that actually works on the synapse. Then we look at activity 5.32. Okay. In the synapse, there are drugs that actually can block or even actually toxins. There's a lot of toxins that actually can works on the synapse. Yeah. Okay. So certain drugs like acetylcholine esterase inhibitor. So basically, it inhibit the acetylcholine from working. Basically, there are none of them being released, so it can actually block the action of the in the synapse. So I leave that to you to look at it on page 77. Yeah, unless you have questions.
I have
Yeah.
On drug acting at synapse. No, just let's say just drug. I was confused when the how should I say this? Is the drug attacking the receptor or the enzyme removing neurotransmitter? Because both of them can result in unfunctional synapse.
Yes, can. Okay, when you talk about choline esterase, then yes, it acts on the acetylcholine. Basically, it removes the neurotransmitters. Okay, but there are certain toxins that actually can also prevent the calcium from going into the cell, or actually sodium from getting into the cell. So it can also work on the receptors. So there are many drugs actually can work on the synapse. So, okay, Shahwan?
Okay, thank you.
So later when we do synapse and you look at botulism, you look at certain teratotoxin on by the pufferfish, especially pufferfish. The Japanese like to take it as a challenge by eating the fish raw. They usually get poisoned by this teratotoxin. Usually if the chef is not good enough, he can get poison from that, and they basically can die from the poisoning when they eat pufferfish. Okay, so I basically have done everything about this module, and you can go to the summary now on page 78. Basically, the summary will basically summarize everything for you there. Okay, and in the summary, basically, we can say 3 things or 4 things basically about the cell membrane function and structures. The most important thing is basically regulating the passage of substances into and out of the cell, and also between the cell organelles and also the cytosol. These are the most important function. Okay. Then the second one, it can detect chemical messengers, so it's able to communicate between cells. Okay. The third one, basically linking adjacent cells together. So basically, these are very important when you look at cancer cell. Cancer cell, there's a loss of this linkage between cell. Because the cell, when they multiply, when they start to get bigger, and when they touch their neighbors, because of this linkage proteins, they basically stop growing. So that also limit the size of the cell. Yeah. And then finally, the fourth one, basically anchoring the cell to the cellular matrix. We talk about integrin that basically allow the cell to communicate with and also basically stop the cell from going further down the basement membrane. Yeah. So this also applies to some of these cancer cells where they become metastasized when they break through the cell membrane. So they are able to basically spread to other organ systems. Okay. Okay. So these are the four most important things. And finally, we talk about drugs that binds on protein and basically on that is on the membranes that can alter the function of the cell chemical reactions. Okay, so these are the last part, and I told you that basically when you later do pharmacology course, this will be very important that you have to really understand how this drug actually works, and most of them are targeting the membrane proteins. Okay, so any questions? I basically done, and you can refer to the page 80 on the flow chart about the cell membrane, and it's already done for you, the summary of the structure of the cell membrane. Yeah, so I'll leave that to you there. Yeah, unless you have any questions on that. Someone responds? Are you okay?
No questions, doctor.
Yes, I do. Anything?
No, I was saying no questions.
Okay, so because you just break off halfway, so probably my line is not very good either. So I just off my video so that you can feel better. Yeah, I just off my video now so that my Wi-Fi will be better. So I think we are done for the class now for this membrane, cell membranes and how helps the cell. So can we do the GRE, the IRE? Basically, it's a feedback session.
Okay, okay.
Okay, so I will share the question with you. Okay, all in, I get 124 response. Okay, so look at question 1. A patient is hyperglycemic in spite of the normal plasma insulin level. This could be due to defect of which of the chemical structure in the membrane of the insulin target cell. So the first one, it says cholesterol. Okay, there are 2 persons who actually answer that. So that is not the right answer. Then we talk about glycolipids. As I mentioned to you, that glycolipids mostly also for cell-to-cell interaction, yeah, or cell-to-cell recognition. The most important thing for glycolipid, they are mainly to recognize the cell as, your red blood cells or your body. The classification is basically the type of blood that you have. There's A, B, AB, or O. These are very important for glycolipids. Yeah. That also about 35 of you answered that. And then the next one, this is not the right answer. Okay. Then 28 of you answered that says is phospholipids. Okay. We know that phospholipid is very important, right? But they are not the site for communication. Phospholipid mainly prevents the molecules or ions from getting into the cell or actually involved in cell-to-cell communication. So they are not. Okay, so as I say, if the cell has only 100% phospholipids, that means nothing get into the cell except lipid soluble molecules, then it won't be very useful. That's why the cell membrane will have proteins. So the last one is basically the protein. That is the right answer. It says that, okay, 59% of you actually answered that. So many of you give answers. Blood glucose was positively related to the cholesterol synthesis in diabetic patient. I don't know how does blood glucose actually positively related to cholesterol synthesis. Okay, cholesterol synthesis is more related to the amount of food that you took in and that is synthesized by your liver. Almost 70% of the body cholesterol comes from the synthesis by the liver. And this, as I say, is actually related more to the amount of sugar in our body, but it's not related to the blood glucose level only. It can also come from synthesis breakdowns of proteins that can also be utilized to synthesize cholesterol. Is that okay? Do you have any question? One? Yeah, tough one. Any question on that? No. I do. No. Okay, I believe you don't. So you are clear now. The answer, the right answer is question. The answer is option D. There's the protein. And why protein is the target? Because there is a problem or defect protein, and proteins, there are a lot of these insulin or receptors. The protein receptors that is present on the cell membrane, and probably the insulin protein receptors that is defective, that is not able to recognize the insulin level. So that's why the insulin level actually increases to try to basically acts on the receptors. Yeah, so there's a defective receptors on the target cell. Do you know what is insulin target cell? Anyone?
The skeletal cell, skeletal cell, muscle.
Yes,
Muscle.
the most important is the skeletal muscle cell because it constitutes about 40%. Actually, insulin receptors are present all over our body cell. But the most important thing is the skeletal muscle cell and also the fat cell, because their insulin receptors, they are being targeted because their glucose transporter are insulin dependent. That depends on the receptors for insulin. Okay, so if the insulin receptors is defective, so this skeletal muscle and fat cell is not able to respond to the insulin level. Shafia, yeah, anyone? Okay, I hope you understand that. Yeah, so I'll just move on to the next questions, unless you have more question you want to ask. No. Okay, question 2. How is cell membrane important in regulating cellular chemical reaction? Is the A option the right answer for you? Okay, A says it's allowed the extracellular matrix to enter into the mitochondria. Okay, to a certain extent that is true, but that had to be regulated, not all. So you have to be very careful with this type of answers, because these are extracellular substrate to enter into the mitochondria. Mitochondria are very much inside the cytosol, the cytoplasm. Okay, so 19 of you answer yes. Okay, then we look at the next one, but this is not the right answer. B, it has a phospholipid to block off entry of steroid hormones. So by now you already know that steroid hormones can diffuse through the phospholipid, so it cannot block off the steroid hormones. Yeah, so this is also not the right answer. Then number D, it has tight junction that allow chemical exchange. That is not true. If you say that tight junction, then chemical exchange cannot happen. So D cannot be the right answer. So the only answer that is correct now is basically C. It has integral protein that can help to activate intracellular enzyme. And this is very important because this integral protein can be a receptors that can activate the intracellular enzyme. Still okay? I think about,
Okay, doctor.
yeah, 38% of you answered that right. So by now, I think you are able to differentiate between those 4 options and you know which are the right answer. Is that true?
Yes, doctor.
Yes. So compared to before you, that means you do the pre-class and now after class, you probably gain the knowledge. Is that true?
Yes, doctor.
Okay. Good. So we are done. Any questions? We probably finished earlier today by half an hour. No? Okay, if not, then I will see you on Monday then. Okay? Akash, you already sent out the attendance to be signed? Or Hamid?
It's the same link, doctor.
Okay, it's the
Yeah.
same link. So can you sign that again and then make sure that it's signed again for the second part? Thank you.
Okay. Thank you, doctor.
Okay, thank you. So I'll see you on Monday.
Thank you, doctor.
Okay, thank you, doctor.
You.
Thank-
Okay,
Thank you, doctor.
thank you.
Thank you,
Okay,
doctor.
thank you.
Thank you, doctor.
Thank you, doctor.
Thank you, doctor.
Thank you.
Thank you, doctor.
Okay.
Thank you.
Thank you, doctor.
Thank you and have a nice weekend, everyone.
You too, doctor.
Thank you to you. I have a lot of things to prepare. Okay. Enjoy your whole weekend then. Okay, bye-bye.
Thank you, doctor.
Thank you, doctor. Thank you, doctor.